Hi and welcome to this video about Windows Subsystem for Linux WSL version 1. And so in this video I want to describe how WSL works. This is kind of a magical thing if you think about it. So first, a little bit of an introduction. What is the Windows Subsystem for Linux? This is a feature that appeared in Windows 10, first in version 16.07, the one that's known as the anniversary update. That was the first beta of the WSL feature, and basically it allows you to run Linux binaries natively on Windows without having to do anything. You don't have to have the source code, you don't have to compile anything, you just take existing Linux binaries and they just run. This is pretty magical, I think, so I want to explain how this magic actually works, so at least some interesting parts of that magic. Now currently WSL has two versions. The first version is version 1, that's the one that appeared initially in Windows 10, and then version 2 came along several years later, and I'm going to focus this video on WSL 1. WSL 2 works in a different way. Technically, if you have WSL installed, you can just flip from version 1 to version 2 or back just by using a command line switch. There's nothing that preventing you from moving from one version to another. Now, you might be wondering what are the differences between these two versions, and you can find that in the documentation, but I'll also mention a few things about WSL 2 at the end of this video. But my focus here is going to be WSL 1. Now, if you're familiar with the idea of subsystems in Windows that were supported back from the very first Windows NT version, there was the OS2 subsystem, and there was the POSIX subsystem, and there was the Windows subsystem. And the idea there was, like in a nutshell, is to take source code that is based on one of those sort of platforms like POSIX, which is a fundamental API in Unix-based systems, and specifically it used the original or the classic subset of APIs. You would need to recompile your application on Windows, get a PE, and then run the application. However, WSL works differently in some way because there's no source code required. You don't have to compile anything. You just take the original binary, which is an ELF binary, that's the format used by Linux systems, and just run it. So it is kind of magical. So let's see what that looks like using tools, and then I'll discuss a little bit more about the details as how it works behind the scenes. So I have WSL installed on my system, and technically once you have that installed, you can use the WSL command with -L and -V just to see what you have on your system. So currently I have two versions of Linux systems on my system. One of them is Ubuntu 20.04, which is using currently version 1, and I also have Ubuntu, which is a more recent version that is maintained by Microsoft, which is using version 2. Technically you can use the option of set version, and you can technically just change the version from 1 to 2 or back for any of the distributions that you have installed. And it takes a few seconds for that to happen. So I'm intentionally keeping one version as 1 because I would like to demonstrate that. So let's go ahead and enter that version. So we can do that in several ways. One of them is to use the WSL command line tool itself. We can use something like the command to run that distribution, or we can just use WSL without any parameters. Since the star here represents my default version, it's going to start this one. Another convenient way, even more convenient, is using the Windows terminal that identifies whatever you have on your system. So you can see I have here Ubuntu 20.04, that's my WSL 1 distribution right now, and Ubuntu is my WSL 2 distribution. This is just something I have on my system right now. So I'm just going to click Ubuntu 20.04 and it will launch the Ubuntu installation here and the system. So I'm currently in Linux. I can do stuff like ls. There's nothing very interesting here. That's because I'm in my home directory. There's nothing there. But we can go to MNT, which is the mount point where the Windows known drives like C are being mounted on. We can go to Windows, for example, and you can do ls to see whatever is there, or ls-l to get a long list of things. I can even go ahead and pipe that into other applications like more or less, if you are familiar with that one. Then I can see things page by page, or just scroll slowly, press Q to exit that. And basically I have a Linux system here. I can go ahead and install new applications using sudo apt install, things like that. Just like any other Linux distribution. In this case it's in Ubuntu, so I'm using apt, but you can use other distributions, and you can just go to the Microsoft Store and just pick whatever distribution you want. There are several options there. Now, what happens here in terms of processes, things like that? What is actually happening? So I can do something like ps just to show the processes that are obtained from this shell. So you can see there are two processes here, bash, which is the thing I'm running right now. That's the classic, well, almost the classic born shell reimagined, so to speak. So we have that born again. And so we have bash and we have ps. So ps is the thing I just ran. So obviously ps is done and bash is still running. You can use aux here, and again, these are command line switches that are supported by the ps Linux command. You can go ahead and use the man command to read about that, or just browse the web if you're not familiar with that. It will show us all the processes currently running on that Linux system. With also the command line there. So obviously there's some init processes here, and there's bash itself and ps, which I've run just now. And so I can see them in their Linux way of looking at things. We can see the PID here. The PID is as far as the Linux kernel is concerned. And so the question is whether you have anything like that on the Windows side. So can we see that on the Windows side in some way? So if I go ahead and launch Task Manager first, that's going to be my first tool, we can look up these process names, like here's init. So here's init. We see there are two inits here, which is what we expect since we have two init processes here. Notice the PIDs are 1 and 11, but here the PIDs are completely different. In fact, these are Windows PIDs, they are not Linux PIDs, but they should match internally. So internally they should be representing the same thing. And you can see that in Windows we know that all process IDs are multiples of 4, but in Linux there's no such rule, so PIDs can be technically anything, like 1, 11, and 12, and 33 that we see right here. And you can see that there are 0 handles in this process. In this process also we can see 0 handles, which again you might think as being weird, but in fact it's not weird at all, and that's because these are Linux processes. So Linux processes are not going to have any handles from a Windows perspective because they have no idea what a Windows handle is. If you think about it, we have a binary that is completely a Linux binary, and Linux binary is going to make system calls just like on Windows. The Windows binary will make system calls into the kernel, and these system calls are targeting the Linux kernel from the Linux process. So obviously these system calls are not using handles. If you're familiar with Linux, these system calls use something called file descriptors as a kind of a alternative, or a different way of representing connection to devices. And in fact in Linux it's almost connection to anything. There's that well-known slogan coming from, I think, Brian Kernighan back in the 70s, that in Linux everything is a file. But in any case, you won't see any handles. You can also see some threads, which again makes sense because there's some code running in those processes, so there must be some threads, at least one, just like we would find on Windows. We also have bash somewhere. Let's find bash. So here's bash, and bash is running in its own process. Here again, there's the Windows number, which has nothing to do with the Linux number. And again, we see there are 0 handles. This is something we'll never see in the Windows process that is still alive, but on Linux we'll see that all the time because Linux has no idea what a handle is. In this case, bash has just one thread, which is of course totally fine. And we can see there's no consumption of CPU. Okay, let's give it one more try. Let's use the dd command. And the dd command is a very powerful command that Linux has. There's no direct equivalent in Windows actually. It allows us to do many things. One of them is to copy from one device to another, one file to another in a kind of a raw binary way. So I'm going to do something simple by taking the input file, that's IF, what's going to be dev0, which is a device that Linux has that when you read from it, it always gives you back zeros. You can continue reading from it until the end of days. It will return zeros all the time. And my output is going to be dev null. So the output is going to go to the null device, which just dumps everything down the drain. So technically, this thing can run forever because the zero device is never running out of zeros, and dev null is happy to take anything you write to it. So I'm going to use ampersand here so I can start that in the background. You can see we have the PID of 34 for that. I can do PS and see that indeed DD is running. I can use the top command to see that I have these processes, and you can see that 100% of CPU time is spent in this DD process, because it's running like crazy, reading from nowhere, or well, reading zeros and writing to nowhere, but it is doing its thing. And if I go back to Task Manager, see what's going on, we should find DD here, and it is running, and you can see right here. And again, it has its own process ID. From Windows perspective, the CPU consumption is 6%, which is roughly 1/16, because I have 16 logical processors. So one logical processor is just like crazy working on this process, doing nothing very useful, but still it is what it is. So from Task Manager's perspective, we don't see a whole lot of interesting stuff here. We can even terminate the process if you want using add task. This would work. Of course, we can do that from the Linux perspective as well. We can do something like we have kill. We know that the PID is 34. We've seen that. We can see that with PS, and of course we can see that here in top. And you can just kill the process, and that's fine. That would work as well. But what happens behind the scenes a little bit deeper beyond what Task Manager can show us? So let's take a look at Process Explorer. So in Process Explorer, we see the same processes just like we've seen in Task Manager. Here's Bash, for example. So we see roughly the same things. However, if we look at the lower pane, in terms of handles, we see nothing, which is no big surprise, but in terms of DLLs, we actually see a lot of interesting things. What we see here are binaries that are Linux binaries. If you look at the actual paths here, well, you can see the names already. We have here the bash binary itself, but then there's some other things here that are being mapped into the process address space. And you can see these SO files. SO, that's shared object. This is the Linux equivalent of Windows DLL. So these are dynamic libraries loaded into the process. You can think of that as part of the APIs that Linux is using. And they're somewhere in my file system. You can see it somewhere there where my Linux distribution is installed. So it's coming from my file system because I am using WSL. It's not a separate virtual machine running Linux. That's not the case. It's part of Windows itself. So it is somewhere here in the file system. So get a bit of sense of what is going on here. If I try to look at the threads here, we see we have one thread. And again, the thread also has some ID, which is going to be, again, unrelated to the thread ID from the Linux perspective. In this case, it's the only thread, so it's actually the process ID should be of the Linux process, going to have just the same one for the first thread, because threads in Linux are kind of different in some respects from threads in Windows, but that's not really important for our purposes here. And so we see that as expected. We can look at other processes, of course, just like before, like init. For example, we might not be able to see something, and that's because Process Explorer takes a bit of a few seconds to refresh its view. So you can see now that we have these two threads within the process of init in this case. And just like in the previous example, pressing DLLs, we can see the DLLs inside this process, in this case, or well, any binaries that are mapped into this process address space. In this case, that's init only, because init has no dependencies. It's the kind of the initial process in Linux. So that's kind of how it works, and well, what we can see, at least in terms of tools. But how does it work? If you think about it, there are two problems here. The first problem is that the format of Linux binaries is ELF. It's not the same as the P format used in Windows. But that doesn't seem to be too bad. I mean, parsing a format, that's not going to be a real challenge, generally speaking. However, the more problematic part is what happens when the Linux binary, since it's already been compiled, it has no idea it's running on Windows actually, is going to invoke various system calls in Linux. So you have system calls like open, for example, or close, or read, or write, or many other system calls that Linux has. Now we know that Windows works in the same way, in the sense that when we use various Windows APIs, they will call NTDLL that would actually invoke a system call as well, which is a way to get to some kernel functionality. So Linux is going to do exactly the same thing. However, the format and the list of system calls is completely different between Linux and Windows. There are different system calls, they have different meanings, they have no correlation in terms of their number, and also the parameters are passed in very differently. It's based on the calling convention that is defined by the platform. So Microsoft provides their own calling convention, and Linux uses a different calling convention, or on something like x64 that we have here. And so if you think about what would happen if a Linux system call reaches the Windows kernel, the Windows kernel will freak out. It will have no idea what to do, and it will fail the system call. So that can't really work. But on the other hand, it does work. So how does that work? So for that, Microsoft had to do some work, and here's what that looks like. If we think about Windows processes, we think about a process in the following way. It's just an address space from a user mode perspective that has a bunch of stuff in it. We have the executable being mapped, various subsystem DLLs like kernel 32, GDI 32, user 32, and so on. We have NTDLL, which is the one that makes the actual system calls. We call APIs that are documented, they're calling NTDLL. NTDLL is going to make the system call, and the system call is being made by putting a number into the EAX register, setting up appropriate parameters using registers and the stack as needed, and then issuing the sys call instruction. And here I'm just focusing on x64. Now, a Linux process will do the same thing, but what we see here in the slide right now, this is the classic Windows process. So essentially, all normal Windows processes look like this. They have these ingredients, they have the process environment block and TBs, there are stacks, there's all these things. And until WSL1 arrived, all Windows processes were like that. We had just one process type, so to speak. So even if we're talking about things like protected processes or UWP processes, all these kinds of nuances on processes, still the main ingredients and the layout is basically the same. We have the same kinds of things. But now with Linux, having a process that has all these ingredients is kind of pointless, because Linux code has no idea what to do with that. Linux code will never use NTDLL, will never look for any subsystem DLLs, will never try to load them to begin with. So something else has to happen here. And so Microsoft came up with this idea called the minimal process. A minimal process is a stepping stone to get to how actually WSL works. A minimal process is just a process with an address space and nothing in it in terms of user mode code or DLLs. There's just nothing there. No NTDLL, no subsystem DLLs, no executables, no nothing. You might be wondering, what is the usage of such a process? Seems to be a very boring process. And so these processes are used by the kernel only. There are two such processes in current versions of Windows. We have the memory compression process and we have the registry process. These two processes are minimal processes. They have data only, and the kernel is the one that's using those address spaces those processes as just a way to location to store information that is interesting for the kernel to manage in a separate process rather than managing that in, say, kernel space. And I'm not going to talk a bit too much about that. This is just not really in scope, but just know that there's these two processes right now, the registry process and memory compression, and such process in general cannot be created by user mode. It's not possible, only the kernel can do that because there's no executable here. So user mode will not be able to do anything there anyway. And so to implement WSL1, what we have here is a third type of process called the Pico process. A Pico process is built on top of a minimal process, so it starts out empty in the sense that it doesn't have any of the normal Windows process ingredients, and this is where the Linux binaries are being loaded. And so this is just normally like mapping binaries as we've seen in Process Explorer. It's just files being mapped, not a big deal. However, what happens when a system call is made by one of these binaries, a Linux application trying to do a system call? So the system call is going to go to the kernel as usual, but a Pico process is just a flag within the process indicating this is a Pico process. And what the system service dispatcher does, the one that decides how to handle the system call, the first thing it does is to see whether the current process is a Pico process. If it is a Pico process, it delegates the request to something called the Pico provider. The Pico provider is just a driver written by Microsoft whose purpose is to simulate the Linux kernel. So with WSL1, in fact, you install the user mode part of Linux, but you don't use the kernel, the Linux kernel at all. In fact, the Pico provider, that driver provided by Microsoft, is the one that does the handling of all these system calls. And this is how WSL1 works. And so the system calls are being diverted to this Pico provider. And it can only be written by Microsoft, only one can be registered and stuff like that. So we can't do something like this. It of course has to be signed in a particular way. And of course, even if we wanted to do something like this as outsiders outside of Microsoft, we couldn't do that because you have to have direct the ability to directly call kernel functions. Not everything that is exported is good enough to implement a Pico provider. It is definitely not. If you're interested, there's some interesting blog posts that have been posted a few years back by the WSL team that discuss some of the things that they were doing and some of the challenges they encountered, because Windows and Linux are not the same thing. Not all concepts are easily transferable. So that's an interesting read onto itself. But this is how WSL1 works. So Windows becomes the Linux kernel. And this is kind of possible because the number of system calls on Linux is not that big. Well, it is pretty big, but not something that is too big to handle. If someone would try to implement the kind of the other way around, try to implement Windows system calls on a different operating system, that would be a major chore because Windows has a lot of system calls. Linux has a lot less, which makes it something which is possible to do. In fact, they've done it. It's not perfect, and that's why WSL2 was created later on, but it still works and works fairly well. So this is kind of the secret of WSL1. This is how it works. And you can look in the kernel debugger and look for that Pico process bit. Is just a bit as part of some of the flags in the eProcess structure. I'm not going to show that, but I'll leave that to you for the interested viewer. So lastly, I want to mention a few things about WSL2. So WSL2 is built in a completely different way. The idea of Pico processes has been abandoned for this purpose, although it's fully supported. Like I said, you could switch between the two versions of WSL on any system. But the idea here is eventually that the best kernel to use to handle Linux system calls is a Linux kernel and not some implementation provided by Microsoft, and that's for many reasons. One of them is the fact that the Linux kernel continues to evolve, and system calls appear, new system calls appear, behaviors might change, and so on. That would make Microsoft's work in trying to keep up with all these changes pretty difficult. And so they decided to switch to a completely different way of working in WSL2 by utilizing something called a hybrid virtual machine. So it's a kind of virtual machine, but still integrated with lots of sharing stuff within the same Windows system. And that's obviously beyond the scope of this video. So anyway, that's WSL1. This is how it works, this magical thing where Linux binaries are able to execute on Windows without any changes.